Dr. Raphael Finkel. For the future, keeping currents, if we don't have talks, I'm not going to fill in any someone else got to do it. But for today, I want to tell you something about work that I did over a number of years, much of it in collaboration with Drs. Trzcinski and Barak, having to do with using answer set programming. They're the theorists, but I'm a programmer at heart. And every day I try to do a little bit of programming just to keep my hand in. So I want to show you just some examples here. And so the example you might know about best is Sudoku. So what I've got is two screens. One is what I plan to do, and the other is where to do it. So I want you to see here that I've got, let's see. So run that again and just tell it that's fine. Okay, so I have a way of a short description of what is a puzzle, and then I use with a Perl program, of course, to generate an answer set program which then gets solved. So I'll show you this working. I've got an example of all dot rank 3. What is an all dot? Well, I'll show you shortly because I can actually run it. So this says build one puzzle of size 3, which is actually 9 by 9, typical Sudoku. And it's not a classic, it's an all dot, which you'll see what it is, and then run it. So that's my spec, and then it just built a puzzle. Now what it did was it first used some constraints to find an arbitrary solution. There are gazillions of possibilities, and then one by one, in an arbitrary order, a randomized order, it removed clues. And when you remove one clue, that you had said with 81 of them, you remove one clue, it's still easy to solve. But you keep removing clues, and it gets harder and harder. And the first clue is, here, it says grounder solved. That meant it was fine. But near the end, we needed the solver. That meant that it was hard. And so at the end, we now have some of those 81 clues left, and I can show you which ones they are, because I can now, it actually built me something which I can run tech on, and here is the puzzle that it ended up with. It's an all-dot Sudoku puzzle, and it looks like an ordinary Sudoku puzzle, but it's got an extra constraint. Namely, because there's a 1 here, you can't have a 1 in any of the other upper lefts. Particularly this guy here cannot be a 1. I don't know if I can use this and talk and use both hands at once, so I'm not going to use this. I'll just try to speak loudly. All right, so that's an all-dot puzzle. So what did the constraints actually look like that it was building? Well, let's see if I can show you that. These are the rules. Now it's using one of several different syntax forms for answer set programming. This is the one that's used by a local product called ASPPS. The people over the years have standardized. This is not the standard at the moment. But what this says is, I'm going to be building various solutions which have a predicate called place. And if you've seen Prolog, you know what a predicate is. It's something which is either true or false. And it's going to have 3 parameters. This is the x-axis, or the row. This is the column, and this is the value inside of it. And I just had to decide that's what I'm doing. So when you have a puzzle that's completely filled out, then there's place 1, 1 has got maybe a 9. Place 1, 2 has got maybe an 8, and so on. And then there are some constraints. Say, for example, that given a particular number that you're interested in, like 7, given a row column ij, there's only one number there. Given all the possible numbers n, only one of them is actually there. That's how you don't put 2 numbers in the same cell. You're not allowed to do that. This 1 at the beginning and 1 at the end means at least 1, at most 1. This says that given a column and a number, it appears in exactly 1 row. This says, they look very similar. Given a row and a column, given a row and a number, it appears in exactly 1 column. This is a more complicated one for small squares, and I'm not going to go into it. Now, for all dot, we also have extra rules. And there's, let's see, was this the all dot rule? Yeah. In every place and every small square is unique. Okay, there was one more special rule for that. And if you can see that very quickly it can solve this many times. It actually solved 81 times to get this solution. And I can do this in different sizes. So if I go back, here's my specification. And I can say, okay, build me a bigger one. And let's do a classic one. Classic Sudoku, but now it'll be Rand 4 is 16 by 16. Have you ever tried solving one that big? There's a few people who like to do it. It's much harder. Oh, let's make it 5 by 5. Why not? 25. These are ones that no one in his right mind would ever want to solve. And again, I will now generate it. Now it's going to take a little longer because it has more things to solve. Each one of these lines floating past is a solution that it was just generating. And at first you see, okay, more and more it's saying I need solver. And near the end, it's most of them. It's pretty near the end. There it is. Now you want to see what the puzzle looks like? Of course you do. There's the puzzle. I'm glad you enjoyed it. What's the solution over here? Right here? I don't know. People can solve this, but no one would want to solve this, it seems to me. So, but that's an example of using answer set programming. And I've got a stable of about 10 different kinds of puzzles that I can generate. And I do automatically every day. It's on my website, webpage. So there are variations on this varying size, varying by adding extra constraints, even varying shape. So I want to show you now something very different called logic puzzles. And so the way I'm going to show you that is by going to a different directory and looking at a particular puzzle. Now, this is already converted into something that the three of us call constraint lingo, which itself translates into answer set programming. Logic puzzles, Dell logic puzzles, you can buy these at the bookstore, and they give you clues. This is an exact summary of those clues, but I'll tell you what the puzzle itself said. Molly has got 6 dolls, and she keeps each doll in a different place in her room. And you tell by looking at the clues what those 6 places are, but I actually have enumerated them here. And each of them wears a different costume. She gives them names. Andy, Esme, Iris, and so on. Here are their names. And each of them has a different color dress. And each one was given to her by a different relative. And the question is, line these up. Esme, what relative? What color? What dress? What place in the room? And there are a bunch of clues that hopefully completely describe it. So the first clue, I didn't write in English, but I'll give it to you here. It says that the doll named Ursula and the one with a Russian dress are the one that has a blue dress and the one given to her by her brother in some order. That is, I don't know if Ursula is the blue one or Ursula was the brother. I don't know if Russian was blue or Russian was the brother. But one of those will work. The next one says, well, the actual clue said, Esme is a different, well, I'm not quite sure how the clue is worded. Let me just say it in English. Esme and Ophelia are different dolls because they have different names, but they are different from the one wearing white, the one given by the aunt, the one on the bookshelf, and the one on the vanity. These are all different dolls. So I've got a bunch of conflicts and a bunch of matches, and it turns out that all of the clues are either conflicts or matches. Some of these, oh, there's one more here. It says that the Egyptian is either gold or silver. But Egyptian is not Yolanda. Yolanda was not the one wearing the Egyptian. And so you got a bunch of clues, and you build a chart, and you play with it, or you're not interested in playing with it. You just want to solve it. So then what you do is you solve it. And that's the solution. It was just generated. And it was done, as you can see, by a pipeline of things. Firstly, I converted it. Here's what I showed you before. I converted that into a format which was then handed to C-Lingo. And the output of C-Lingo, which is a constraint solver, an ASP constraint solver, was given to a formatter which was specific to this kind of puzzle so that I could print it out nicely. So what was actually the constraint, what was the program that it generated? Well, let me show you this. This is what it actually generated, nicely commented. So the first one was match Ursula Russian Blue Brother. Well, there's a bunch of prologue-like rules, but they all start with that symbol, which implies that there's nothing on the left-hand side. Now in prologue, there's a left-hand side, which is the result of what happens if the right-hand side is true. If the left-hand side is empty in answer set programming, it means this must not happen. And so this is a constraint. It must not happen that the right-hand side is true. Namely, that the color doll blue Ursula, I introduce these cross-category predicates. Color doll blue Ursula, if that's true, that means that the color blue is the doll, is the name Ursula. Well, if that's not the case, and it's also not the case that Ursula brother, then there's a problem. In other words, Ursula must be either blue or brother. This says color costume blue Russian, costume relative Russian brother. This says that Russian is either blue or brother. And so for every pair of categories in alphabetical order, I build a two-part predicate. All right, how about this conflict? That was easy. It says that I know that Esme and Ophelia are different dolls because they are different names. However, the color of doll, white, Esme, cannot happen because Esme cannot be white, and it also can't be given by the ant. Well, you'll find that here. Doll relative Esme ant. If that happens, there's a failure. So it's a bunch of constraints. And all those constraints then pretty much define the problem, except for some boilerplate at the bottom that defines what does it mean for color doll to be true. Color doll is true if there's a color location, a doll location, and everything is of the right type. I'm not going to go into the details. I'll be glad to discuss the details offline with you. But this is kind of neat. You can solve these puzzles. I don't like solving puzzles. I like writing programs that solve them for me. I'll give you one more example. It's called Back to School. All right. So there's a bunch of kids, Beth, Tabitha, Rich, Joy, and Steve, and some are girls and some are boys. So I call it a partition as opposed to a class. For a class, every row has exactly one value. I'm sorry, every column has exactly one value. For a partition, some will be one, some will be the other. And I agree that Beth, Tabitha, and Joy are girls, and Rich and Steve are boys. Other things I've got kids, girls, kids, items, writing, color for this and that. All right, this says that the mechanical pencil, the wood pencil, the colored pencil, and the red R, whatever that is, have got to be different rows in the result. So actually I gave these two in English. The 5 kids are the girl who got the alarm clock, the one who got the orange ruler, the one who got the felt tip pens, Joy, and the one who got the green binder. Well, those are all in conflict then. Green B is green binder. And I say that the clock must be a girl. So I can translate each of these English sentences. As I read more and more of these puzzles, I introduce more and more of these notations. And then I can just run it. So let me just run that one. All right, there's the solution. And you can see that it took less than 1/100 of a second. It turns out that the blue binder has the orange ruler, and it's a boy, and it's a colored pencil, I guess, and the kid is named Rich and uses a ballpoint. That's the solution, and there's only one solution. I asked for 2, it found 1, it must be unique. Well, other puzzles. All right, let me show you some other puzzles. I spent a sabbatical year at University College Cork in Ireland, and I spent a lot of time just playing with various kinds of puzzles there. And I'm going to show you a few of them. One of them is snake. So I just picked a few of them here. And the job of Snake is you've got an m by m board, and it's to be filled by the numbers from 1 up to m squared, but adjacent numbers have got to be next to each other, and a rook's move. Actually, it's got to be a king's move, I think is the way I did this. Let me show you a solution first, and then we'll look at the program. Now I'm asking for a size 12, so here's a 12 by 12 solution. So here's 1, 2, 3, 4, 5, 6, 7, 8. Now, of course, this isn't hard at all. You just go like that. But that's cheating. I want to give you the constraints of how to do this. I might be interested in knowing how many solutions there are. Now, at this size grid, it's going to be several gazillion at least. Not quite infinite, because in fact, most integers are large. But how did I do it? Again, I have this representation using place. Place ijv means that v is the value placed at ij. And every cell must be covered by a single value. And I'm using a slightly different notation here. This is more like the standard notation that people have chosen. It says that if I and j are both numbers that are in the range between 1 and n, it is column and row. Given a column and row, considering all the possible values I might put there, at least one value must be there, and at most one value is there. That is, one value in every place. And every value must be there once. So I say, given a value, there is exactly one place that has that value. Now there's the adjacency rule. This is the last rule. I did it in 3 rules. So if you were to write a program in C that generated this, well, of course, you would just make it go like that. But if you, in general, if you wanted to show the rules, it would be much more complicated. In answer set programming, you can often say things very compactly, and then you just depend upon the solver to handle it. And this says it cannot happen that, that's the constraint, that I've got some value in some place, and I don't have the next value in an adjacent place. One higher that way, one lower that way, one higher that way, one lower that way, given that v is a value, and so on. So it says, it cannot, given a value somewhere, it cannot be that the next value is in a bad place. That's the entire program. Let me show you another one now. Custos. Again, I'll show you the solution first, although the solution is not going to be very useful. There is the solution, the first solution, at size 15. I asked it for size 15 here. And as you see, I use makefiles because I can never remember how to invoke stuff. Put everything in a makefile, and your life is so much easier. So, this is a solution to the Custos problem. And I show it 2 ways. One is that way, and another is as permutations, because for technical reasons, I sometimes want to see that. It's a permutation of the numbers from 1 to 15, in this case 15, with a special property. There are 15 factorial permutations, but very few of them have the property that I want. The property is if you draw a matrix, and in every column you show, let's say my permutation starts 1, 2, 3. Then I would have a 1, a 2, a 3 in the first positions in the Y. So I'm just going to have a bunch of dots. And every column will have 1 dot, every row will have 1 dot. That's a permutation. But the Custos constraint is if I draw a vector between any 2 dots, that vector is unique. You'll never see that vector anywhere else. So in fact, 1, 2, 3 is illegal, not allowed, because the vector from 1 to 2 is the same as the vector from 2 to 3. That will not happen. And so there are lots of solutions. If I ask, for example, let's make it size 5. And I'll say, show me all the solution. Solution source is 5 and all. All right, there are only 9 solutions at size 5. Is there a solution at size 32? No one knows. How big is the problem? Big. It's been, you've heard perhaps David Vulach, my high school advisee, working on this. and he's been running this on a set of high CPU count computers for months. We're unlikely to find a solution, even if there is one. But anyway, that's the problem. Now, what does it actually look like? The problem itself has just a few rules. The most important rule is I have to decide what is the delta between any 2 points, and then having computed that, I say that there's at most one delta available across the entire set of possible deltas. Each possible vector appears 0 times or 1 time, but not more than that. And that's the entire program. Well, the entire program goes on a little bit, but much of that you'll see is commented out. Let me show you Ramsey. This is a fun one. First, let me actually make it. This says, find a solution to Ramsey, whatever it is. That's named after a mathematician, Philip J. Ramsey. I made up the Philip and the J. What's it, actually? Okay, Philip J. Ramsey. I'm going to ask for a size 12 Ramsey. And here's the solution. Isn't that nice? It's a graph. It's a non-complete graph. Well, what I'm looking for is a graph that has no 4 click and has no 5 anti-click. That is, it can't have 5 vertices that are independent, and it can't have 4 vertices that form a click. Now, it's obvious by inspection that this is that's not obvious at all. You just have to take my word for it. Let me ask for it of size 5 instead. That was size 12. Let me try one of size 5. All right. There's the solution of size. Now, there should be no 4 click. I think that seems to be true. The only thing that could be in a 4 click is 3, because it's got 4 outputs. Now, I guess that's not a way of solving it. Anyway, that seems to be a solution. What does the program look like? Well, this is one that actually Victor worked on, so I'm just stealing his result here. Here's the program. I had to modify it slightly in order to fit the new syntax, but I'm saying that red-blue is either 0 or 1. And color XY of some color means if I've got a vertex X and vertex Y, if color is 0, that means there is a line between them. If it's 1, there isn't. Given that vertex X and vertex Y, and X less than Y, you can hardly see the less than, but that's what that says. Because I don't have to worry about directed graphs, so I'll keep X less than Y. And this says at exactly 1, again, at most 1, at least 1, or at most 1. Possible colors. So every X and Y is connected by a line of some color, red or not there at all. And then there's a constraint here saying that if I've got a bunch of zeros, that is red lines between X and Y, X and Z, T and X, X and Y and Z, T and Y, and T and Z. In other words, if I've got what looks like a 4 click, it's a constraint. It can't happen. Not allowed to happen. And again, there's a bunch of less thans here, so I don't look at duplicates. This is the anti-click. There is no anti-click of size 5. That's the entire program. And so I will conclude by showing you this one more time with a big number, 20. There it is. Aren't you glad that you've now seen a solution to this Ramsey puzzle of size 20? Now, if you have any questions, you want to see more puzzles, come visit me in my office. I'll be glad to speak to you. Are all the pizzas gone? Someone's standing next to the pizza there. Is it all finished?
I think so, yeah.
Yes, good. Then it's a success. I'll see you next week if someone signs up to speak.